So, new room, baby, new room. x86 architecture overview. Malware often works by abusing the way systems are designed. Therefore, to understand how malware works, it is essential that we know the architecture of the system they are running in. In this room, we will get brief overview of the x86 architecture from the malware analysis point of view. Please know that there might be a lot of details of the x86 architecture that we will be skipping over, but that is because they are not related to malware analysis. Learning objectives. Summing up, we will be covering the following topics in this room. Overview of the CPU architecture and its components, different types of CPU registers and their usage, memory layouts as viewed by a program, stack layout and stack registers. So let's dive into the room and learn about mentioned topics. So CPU architectures that most widely used in this from the von Neumann architecture. A brief overview of the architecture is demonstrated in below diagram. CPU registers, we have arithmetic, logic unit, control unit, main memory, RAM aka RAM, input-output devices. This diagram shows that CPU has three components: arithmetic logical unit, aka ALU, the control unit, and register. The CPU interacts with memory and I/O devices outside the CPU. Let's learn about each of the components mentioned in the diagram below. Control unit. The control unit gets instruction for the main memory, depicted here outside the CPU. We are talking about control unit, this one. Okay, now the address to the next instruction to execute the store in the register called instruction point, or IP. In this 32-bit system, the register called EIP. In the 64-bit system, it's called RIP. Arithmetic logic unit. The arithmetic logic unit executes the instruction fetch from memory. The result of the executed instruction are stored in the register or the memory. Registers in the register are CPU storage. Registers are generally much smaller than main memory, which is outside the CPU, and helps save time in executing instruction by replacing important data in the direct access to the CPU memory. The memory, also called memory or random access memory, aka RAM, contains all the code and data from the program to run. When the user executes the program, its code and data are loaded in the memory from the CPU. One instruction accesses it at the time. I/O devices or input-output devices are other devices that interact with computer. Those devices include cable, mouse, display printless mass storage like hard disks, USB, etc. In short, when a program has executed, it is loaded in memory. From there, the control unit fetches one instruction at a time using the instruction pointer register, and arithmetic logic unit executes it. The results are stored in either registries or memory. In which part of one Neumann architecture are the code and data required for program to run stored? In which part of one Neumann architecture? Registers, I guess. So registers, memory, execute in place. Memory contain data, code and data required program to run stored. Memory contains all the data user executes. Memory. Boom, baka. What part of the CPU stores small amount of data? What part of CPU small amount of data? In which unit are arithmetic operation performed? Arithmetic logic unit. This is it, and this is a guess. This is registers small amount of data. Yes, it is. Registers overview. So register are the CPU storage medium. The CPU can access data from the register quicker than any other storage medium. However, its limited size means it has to be used efficiently. For this purpose, the registers are divided into following different types: instruction pointers, general purpose registers, status flag register, segment register. Let's go through each of those registers one by one below. The instruction pointer is the register that contains the address of next instruction to be executed by CPU. It also called a program counter. It was originally a 60-bit register in the Intel x86 processor, from where the term x86 originated and then abbreviated as IP, instruction pointer. In 32-bit processor, the instruction pointer became a 32-bit called EIP, or extended instruction pointer. In 62-bit systems, this register became 62-bit called RIP. Here, so the R here stands for register IP. I don't know. And they have some more meaningful, like register IP. Okay. General purpose register. The general purpose register in the x86 system are all 32-bit register. As the name suggests, they are used during general execution of instruction by CPU. In 64-bit system, those registers are extended. A 64-bit register, they contain following register: EAX or RAX. So first will be 32 bit register, and second will be the 62-bit register. In this accumulator register result of arithmetic operation are often stored in the register. The 32-bit will be EXE register present, while 64-bit REX register is presented in 64-bit. Okay, just as I said. The last 60-bit of this register can be accessed by addressing EAX. So we have EAX divided to AX. So we have EAX, this one, and then RAX. Okay, so the second one is base register, which often used to store base address for referencing offset. Similar to EAX RAX, it can be addressed as RBX, EBX, so the same. The third one will be counter register, often used to counting operations such as loop, etc. Similar to above, two register have different versions of it: 64, 32-bit, 60-bit, 8-bit, and so on. EDX, RDX, called data register. It's often used multiplication division operations similar to the above. Okay, so the next stack pointer, it points to the top of stack, and it is used to in conjunction with stack segment register. It is a 32-bit register called ESP. Okay, and the 64-bit register, RSP. Okay, no brainer here. EBP, ERBP. The base pointer, it is used to access parameter passed by stack. It is also used to in conjunction with stack segment register. It is okay, 32 and 64-bit. ESI, RSI, source index register. It's used for storing for string operation. It is used with data segment DS register as an offset. REDI, RDI. Destination index register. It's also used for string operation. It is used with extra segment ES register as an offset. It is 32-bit. Okay, R8 through R15. General purpose registers are not presented in 32 bits. Are not presented. They are introduced in 64-bit system. They also addressable in 32, 60, and 8 modes. For example, for the R8 register, we can use R8D for lower 32-bit address, R8W for lower 60-bit address, and R8B for lower 8-bit address. Here the suffix D stands for double word, W stands for word, and B stands for byte. Okay. Which register holds address next instruction? I guess pointer. Clear as mad. This one. The instruction pointer. That's it. Which register 32-bit, also called counter register? The counter register. Generate pose, accumulator, base counter are x86 counter register. Wait, what? Which register from one discussed above are not presented in these ones? Are presented in the 32-bit. Just read about it. That's it. Registers continue. So now we have the start flag register. When performing execution from indication about the status, some indication about the status of the execution is sometimes required. This is where the status flags come in. This is a single 32-bit register for 32-bit systems called E-flags, which is extended for 64 bits for 60 are flags. The status flags register consists of individual single bit flag that can be either one of the some of the necessary are discussed below. Zero flag denoted by ZF. Zero flag indicates when the result of the last executed instruction was zero. For example, an instruction is executed that subtracts the RAX from itself. The result will be 0. In this situation, the ZF will be set to 1. Carry flag denoted by CF. Carry flag indicates when the last executed instruction resulted in the number too big or too small for destination. For example, if we add hexadecimal number with all F's to the hexadecimal number with 1, we will get and solve the result in 64-bit register. The result will be too big for the register. In this case, CF will be set to 1. Sign flag. The sign flag SF indicates that the result of operation is negative or most significant bit is set to 1. If these conditions are met, CF is set to 1, otherwise it's set to 0. Try flag. The try flag indicates if the process is debugging mode. When TF is set, the CPU will execute one instruction at a time. For debugging purposes, this can be used by malware to identify if they are being run in debugger. So we have general register that we just walk through. Segment register CSSS, DSES, FS, GS. EF flags for the 32-bit, I guess, and instruction flag ERP RIP. Segment registers. Code segment register points to the code segment. Memory data segment DS. Stack segment register points to program stack memory. Extra segment ES, FS, GS. The extra segment register point to different data sections. Those DS register divide program memory into 4 distinct data sections. Which flag is set used by program to identify is debug? TF something trap flag, debugging mode trap flag TF. Which flag is set the most significant bit of the operation set to most significant bit? I guess we are in the carry flag. I guess. Let me see. Most negative. Most significant bit. Okay, sign flag. So then carry flag. Oh, okay. Sign flag. Which segment register contains pointer to the code memory code segment CS. Okay. So now we have memory over. When program is loaded into the memory in the Windows operating system, it sees an abstracted view of the memory. This means the program does not have access to the full memory. Instead, it only has access to its memory. For the program, that is all the memory it needs. For sake of brevity, we will not go into the details of how the program operating system perform abstraction. We will look at the memory as the program sees it, as that is more relevant to us when reverse engineering malware. The diagram here is an overview of the typical memory layout for the program. As can be seen, memory is divided to different sections, namely stack, heap, code, and data. We can see main memory, stack, heap, code, and data. While we have shown 4 sections particular order, these can be different from how they will be all the time. Code section can be below the data. We can find brief overview of 4 sections. Code section, as the name implies, contains the program code. Specifically, the section refers to the text section of the portable execution file, PE, aka PE, which includes instruction executed by the CPU. This section of the memory has executed permission, meaning that CPU can execute the data in this section of the program memory. Data. The section contains utilized data that is not variable and remains constant. It refers to the data section portable executable file, aka PE. Contains global variables and other data that are not supposed to change during the program execution. Heap. The heap, also known as dynamic memory, contains variables data created, destroyed during the program execution. When variable is created, memory is allocated for the variable at runtime. And when that variable is deleted, the memory is free. Hence, the name dynamic memory. Stack is one of the most important parts of the memory for the malware analysis point of view. This section of the memory contains local variables, arguments passed on the program, and return address of the parent process that called the program. Since the return address is related to control flow of CPU's instructions, the stack is often targeted by malware to hijack the control flow. You can look at buffer overflow room we will look to learn how this happens. We will cover more details about the stack next task. When a program is loaded in the memory, does it fool you? Yes or no? Nope. Which section of the memory contains code? Code section. Which memory section contains information related to the program control flow? I guess program control flow. I guess stack. That's it, baby. So now, stack layout by program memory that contains argument passed to the program, the local variables, and program control flow. This makes stack very important regarding malware analysis and reverse engineering. Malware often exploit the stack to hijack the control flow of the program. Therefore, it is important to understand stack, its layout, and its working. The stack is the last in, first out LIFO memory. This means that the last element pushed into the stack is the first one to be popped out. For example, if we push ABC into the stack, when we pop out those elements, first pop out will be C, B, and then A. CPU uses two registers to keep track of the stack. One is the stack pointer, the ESP or RSP, and the other is base pointer, EBP, RBP. The stack pointer points to the top of the stack. When any element is pushed to the stack, location of stack pointer changes to consider a new element that was pushed into the stack. Similarly, when an element is popped off the stack pointer adjusts itself to reflect that change. So we have stack arguments, variables, stack. Okay, the stack pointer itself, the base pointer. Okay, stack pointer we've just reflected. The base pointer for any program remains constant. This is the reference address where the current program stack tracks its local variables and arguments. All base pointer and return address. Below the base pointer lies the old base pointer of the calling program, the program that calls the current program, and below the old base pointer lies the return address, where the instruction pointer will return once current program execution ends. A common technique to hijack control flow is to overflow a local variable on the stack such that it overwrites the return address with address of the malware author choice. This technique is called stack buffer overflow. So once more, a common technique to hijack control flow is to overflow local variable of the stack such that it overwrites the return. Okay. So we are moving the variable to the place of the return address. So let me draw it real quick. So let's say we have two arguments, and now I want to rewrite the return address. So I will push the return address with my new argument, and then I will stack buffer overflow because I've just lose the return address to this one. I hope it makes. So the technique is called common technique buffer overflow. Argument being passed to the function are pushed to the stack before the function starts execution. Those arguments are present right below the return address on the stack. Arguments safety VP function prolog and return address rate EDP. Okay, function prolog and epilogue. When function is called, the stack is prepared for function to execute. This means that the argument are pushed to the stack before start of the function execution. After that, the return address and the old base pointer are pushed into the stack. Once those elements are pushed, base pointer address is changed to the top of the stack, which will be the stack pointer of the caller function at the time. As the function executes, stack pointer moves as per requirements of the function. This portion of code that pushes the arguments, the return address and the base pointer into the stack and rearranges the stack and base pointer is called function prolog. Similar, the old base pointer is popped off the stack and into the base pointer. When the function exits, the return address is popped into the instruction pointer and stack pointer is rearranged into point of the top of the stack. The part of the code that performs this action is called function epilogue. Click the to view button at the to split. Okay, let me do this one. And instruction: drag and drop stack bases on the left to create stack position. Okay, so stack register. Follow the instruction to attach static site and find flag. What is the flag? So now hop attach static by. So we have stack. Argument 1, argument 2, return address EBP. No. Caller EBP. Valuable 2. Safety EBP. ESP. Do what? Restart. Do. What's going on in here? So 1, 2, 3, no, 4, 5, 6, ESP. Wait, what? Registers. I don't know what I'm supposed to do here. Nope. 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 Wait, what? I don't know what I'm supposed to do. To the register? I don't know. Let me check this one real quick. Okay, I just got this one and I frankly don't know what I'm supposed to do. I don't know. Okay. 1, 2, 3, 4, 5, 6. This one and that one. Okay. Now I think. Okay. That's it. Okay. That's it. Thanks. Have a nice one.